So it's a pleasure now. I think most of you are back, and it's a pleasure now to introduce our next speaker, Luca Davi, who is a professor at the University of Duisburg-Essen. Luca has done work on runtime attacks and not only just constructing attacks, but also providing defenses on systems. He had a number of impactful work specifically towards practice. That means a number of companies like Intel, like Microsoft, and related companies like Qualcomm, they have acknowledged his work because they had a very big impact on their products. Specifically, for example, in the case of control flow integrity for Windows, I remind you on Emmet tool, but also he had work on iOS, attacking iOS systems, making defenses against runtime attacks, code reuse attack on embedded systems. Luca has also received for his PhD, received the ACM Zigzag Prize, which is actually a very prestigious international prize provided by ACM to honor his work and effort. He's a rising star in our community, and he's going to talk about are there trusted execution environments that are, from my point of view, very important for building trusted systems. Are they important, and how secure are they when they are built into our real system? So look at the stage is yours.
Thank you, Ahmad, for the very nice introduction. It's a great pleasure to speak at this workshop. Today, there is a strong need for protecting sensitive data, but not only sensitive data, but also there's a need to protect code because of intellectual property reasons. And considering that a lot of data and code is moved to cloud providers and cloud servers, we need some mechanism to protect our data and code. And as you have seen in the last talk by Serjan, trusted execution environments play a dominant role here because they provide a very strong isolation between applications running in the normal world, the untrusted applications, and applications that are strongly isolated in a secure world. Sometimes you have a trusted operating system, and these new hardware technologies have made a significant step towards securing data and code. Especially the attacker who compromises applications, user applications, or operating system in the normal world has no direct access to applications and operating systems in the secure world due to the hardware-based isolation. As you know, there are several TE implementations. Most popular are ARM TrustZone and Intel SGX. I will be focusing in this talk on Intel SGX. I think this fits also very well because Serjan was presenting his research on ARM. The focus of this talk will be on software-based attacks. So what can go wrong if your applications in the trusted secure world have a program error? If an attacker can exploit these errors, then of course he's able to undermine the hardware-based isolation. However, the question is, how can we really construct attacks against code and data that is running in the secure world, and whether there is a potential vulnerability that we can exploit? So to get everyone on page, I will quickly provide some background information on software-based exploits with the focus on memory corruption attacks. And then after that, I will present you our work on constructing exploits against trusted execution environment code, and also our work on how to automatically find vulnerabilities in TE code. It all started with the Morris Forum in 1988. which infected 10% of the machines that were at that time connected to the internet. And as part of the attack, there was a buffer overflow exploit, allowing the attacker to corrupt control flow information like a function pointer or return address on the application stack. In 1996, a very famous article by Aleph1 was published, Smashing the Stack for Fun and Profit, where Aleph1 demonstrated how to inject code into an application, exploit a vulnerability like overwriting a return address and then executing the malicious code. In 1997, the first code reuse attack was published. In contrast to code injection attacks, this attack reuses existing benign code of your application to induce malicious operations. However, the attack was limited to 32-bit systems. So in 2005, Kramer showed how to also apply this to 64-bit system, where the main challenge was that 64-bit system provide function arguments by the means of registers instead of the application stack. So Kramer needed to do some tricks like executing some function epilogue sequences to induce malicious behavior. However, these attacks were mainly focusing on executing one or more functions that are available in your application. And they could not allow arbitrary code execution, which is the case for standard code injection attacks like we have seen in 1996. So Horav Shacham, he presented in 2007 an attack technique called return-oriented programming, which is now the state of the art in exploitation techniques when it comes to exploiting bugs of your Acrobat Reader or of your applications in embedded systems. Return-oriented programming plays the predominant role. And from there on, there has been a continuous arms race between attacks and new defenses trying to mitigate those attacks. In general, we can think of these attacks as follows. Every program can be abstracted through its corresponding control flow graph. The nodes in this graph represent code blocks, and edges represent control flow transitions like a jump or a function call. If the application has a bug, then the attacker for a classic code injection attack injects some malicious code into the data space of the application, overrides some function pointers, and the consequence is that the control flow is redirected to the currently injected code. Today's systems do a good job in defending against this classic attack by providing data execution prevention. This is the name that is used for Windows-based systems, where the idea is that you mark code pages as non-writable, meaning that an attacker cannot inject code and at the same time set the memory page where the code has been injected to executable. That is why from 2010, attackers moved to return-oriented programming, where the idea is you still corrupt code pointers, but you no longer inject any code. You rather exploit existing nodes in your application, for instance, by moving the control flow from node D to E, and considering modern applications which link to a number of libraries, there are many, many code blocks that you can use and combine with each other to basically get the same malicious behavior as you would for classic code injection attacks. So what can we do from a defense point of view? There are two main directions. Both of them assume that programs will have vulnerabilities, so they are not focusing on eliminating vulnerabilities, but they rather say, okay, programs stay complex, they use native code, so we have to deal with vulnerable code. What can we still do to mitigate an attack? The first one is called code randomization, where the idea is to randomize all code blocks in memory. So when the application is loaded into memory, every code block gets a fixed position, and code randomization or fine-grained code randomization tries to randomize the order of the code blocks so that an attacker can no longer know where the code is located in memory. He can only do a guess. In contrast, a proactive defense called control flow integrity marks each code block with a unique label and then instruments each of the control flow transitions to ensure that the application at runtime follows a legitimate path. Like in this example, code block C needs to target code block E. And both of these techniques have found their way in modern systems. So if you run a modern Windows systems, you have some form of CFI and some form of code randomization. In this talk, I will be mainly focusing on code randomization because code randomization has been also applied to TEE code, which made it for us interesting to see how effective it is. As I said, we will be focusing on SGX. For those of you who don't know SGX, it's a trusted execution environment technology which allows application developers to outsource or to move privacy-sensitive data and code into so-called enclaves that are embedded in the so-called host application. And even if there is a malware that has been injected on the PC, and the operating system has been compromised by exploiting a kernel vulnerability, the attacker has no means to access the enclave memory because the enclave memory is integrity protected and also encrypted. So this is a quite effective defense. However, enclave, as you have seen, they sit in the application memory. And of course, the host application needs some way to communicate to the enclave. This is where the Intel SGX SDK comes into play because it provides some interfaces where application code from the host application can access functions and data of the enclave memory. But they are really good protected because you can only access the enclave code from predefined public interfaces. By contrast, the enclave sitting in the application memory can access all memory of the host application. And the enclave is also a bit limited in the way that you cannot perform system calls directly. So you should only really process your secret code and data inside the enclave without providing too much complexity and functionality in the enclave. So let's look at the first memory corruption attacks. As you may know, there is a lot of research on circumventing SGX protection based on side channels. This is not our focus. We want to see whether software-based vulnerabilities can be exploited in the context of SGX. One of the first attacks published at Usenix Security 2017 demonstrated that you can launch a return-oriented programming attack even if you have no clue about the code that is running in the enclave. So if you have an encrypted enclave binary, which you don't know, the attack tries to find some interesting gadgets, meaning some interesting code blocks that could be leveraged for a return-oriented programming attack. However, because this attack is based on guessing some code blocks, a wrong guess leads to a crash of the enclave. So you need to restart the enclave, and as long as there is no randomization, so the memory layout is static and fixed, this attack still works. However, if you apply code randomization as SGX Shield has demonstrated, then these attacks no longer work because for every crash of the enclave, a new memory layout is instantiated once the enclave is loaded. So we asked ourselves the question whether it's possible to still exploit and undermine randomization in SGX enclave protected by SGX Shield. And unfortunately, this is really the case, mainly because the Intel SGX SDK provides some functionalities which cannot be randomized or hardly be randomized. And these very basic functionalities are already sufficient to perform arbitrary attacks against enclaves if there is a vulnerability inside the enclave. To show you how the attacks work, let's take a deeper look how the enclave communicates with the host application. Here you see we have the enclave code consisting of 4 functions. And there are 2 basic libraries provided by the Intel SGX SDK, the so-called TRTS, which is located inside the enclave memory, and the URTS, which is outside the enclave memory. So once an application wants to call an enclave function, it issues a so-called eCall. That eCall is delegated to the URTS. The TRTS then resolves the function call and is responsible for executing the function of interest, in this case, function 0. The enclave can also invoke functions in the host application, and this is also routed through the TRTS and URTS. The main instruction for doing this is a so-called OCall, outer call instruction, which is delegated to the TRTS. And now the interesting part when an OCall happens is that the register state, meaning the execution context of the current enclave execution, is stored on the enclave stack, the application data memory of the enclave, to allow accurate reset of the execution state once the application code has finished executing the desired function. So after storing the register state in a so-called OCall frame, the TRTS invokes the URTS, and then the application code is executed. There is also another way of exiting an enclave. It's called the EAX, asynchronous enclave exception, where the idea is when an exception happens, like a division by 0, an EAX is issued that is delegated to the operating system. The operating system then goes back into the enclave memory to store the current execution state, and then later on handles the exception based on predefined exception handlers. In both cases, restoring the state is a critical part here. As you have seen, both for OCall and EAX, the register state is saved on the enclave stack. If an attacker can access the enclave stack, because it's just a data memory by means of exploiting a vulnerability, then he can control the register state. And once the OCall returns or the exception has been correctly handled, then the malicious register state is loaded. There are 2 different functions for performing the restoring of the register state. If you have an OCall frame, there's a function called ASM ORET. And if there is an exception through an EAX instruction, then there is the continue execution function. And these 2 functions are not randomized. And we can then perform an exploit that leverage these functions to gain arbitrary code execution. The register state differs slightly from for OCalls and the exception information structure. You see here in blue boxes 64-bit registers. Of particular interest is, of course, the RIP register, which stands for the instruction pointer. If an attacker can control that register, the attacker is able to call any code of his choice. For the exception information structure, we even have more registers available. So it's kind of a bit more powerful than the OCall frame, but the attack works for both exception information structure and OCall frame. So I already said that if an attacker can inject fake exception structures or fake OCall frames, he basically controls the execution of the enclave. How would this in general work? You have a vulnerability, for instance, a buffer overflow vulnerability in your enclave code. The attacker constructs in the host application fake state information structures and exploits the vulnerability to either directly inject the counterfeit state into the enclave state, or let the enclave believe that the counter state information is in the host application, and then restore the state from there. And once the enclave uses this counterfeit state, any function of the enclave code can be executed, or basically any code block inside a function can be executed. Now, for performing the attack, we need to think about two prerequisites. For the ORAD primitive, so meaning for the OCall frames, we need control of the stack. So we need a vulnerability on the stack. This might not always be the case. Usually for modern software, we usually find vulnerabilities that are more related to heap overflow vulnerabilities. And this can be satisfied by the continue primitive for the exception information structures, where we only need control of a function pointer, but additionally control of the RDI register, which is just a register on 64-bit systems. Now, the beautiful part of this is that we can combine the two to gain full access on the register state, because as you can see, for the ORAD primitive, we only need control of the stack pointer and the instruction pointer, and it allows us to set the RDI register. So we can execute them combined to basically get control of all the registers that are available. And once an attacker gets control of those registers, he can then mount any attack of his desire. So how would this work? For stealing a cryptographic key, we would inject the counterfeit state. We would exploit the vulnerability in function 0 here to get control of the instruction pointer, and we redirect the control flow to the ORAD primitive, which is exactly the function responsible for restoring the state after an OCall happens. The ORAD primitive is only used to set the RDI register and then transfers execution to the continue primitive. And the continue primitive then sets all the registers, and finally we can invoke the function that the attack is based on. In this example, get the key. So we load the key into the enclave stack, for instance. Then again, we go through the combination of ORAD and continue to get to the next function in this example, which would be a just send file function that we abuse to set the to load the cryptographic key out of the enclave into a file that is accessible by the attacker. However, if SGX Shield randomizes all the functions inside the enclave, this attack would no longer work, because even if we have the ORAD and continue primitive, we don't know where the functions are located in enclave memory. And as I told you before, crashing the enclave is also not an option, because once the enclave is initialized again, all the functions will be re-randomized. However, in SGX version 1 especially, we have another interesting code block inside the TRTS, which allows us to perform targeted memory writes. And these targeted memory writes are able to write new malicious code inside the enclave memory, because in SGX version 1, there is enough memory that is marked as readable, writable, and executable, which allows us to even run a basic code injection attack to inject code that would steal the cryptographic key out of the enclave. So what you can see here is a kind of hybrid exploit. You first use return-oriented programming to invoke the memory write gadget. And once you have the memory write gadget, you inject code into the enclave memory, and that injected code performs the malicious operation. So what can we do to defend against this attack? Of course, one obvious idea would be to remove the SDK from the enclave memory. However, this is not really an option, because the interface for invoking functions inside an enclave requires the SDK, especially for OCalls, eCalls, and EAX instructions. Another way would be to randomize the TRTS. This, we looked a bit into this. This turns out to be quite challenging, because the TRTS is accessed through fixed entry points. So another idea would be to discover vulnerabilities beforehand. And this is a research direction we followed over the last year. And our main questions that were the main focus of our research were to find how likely is it that there are memory corruption vulnerabilities in SGX enclaves, because the attacks that I demonstrated you before were all based on toy, let's say, toy vulnerabilities. We just assumed that there is a vulnerability. So it might be that SGX enclaves are developed with security in mind, because this is very security critical code. There are many testing procedures, and the code is not as complex as a web browser, as I told you, because there are system calls are not allowed. So there could be a good chance maybe that there are not so many vulnerabilities available. And second, we wanted to develop an automated analysis approach, because manual analysis is time consuming, and of course we might miss bugs. The critical point for finding vulnerabilities is the interface from the host application to the enclave, because the enclave performs computation on secrets, but it relies on untrusted data that is provided by the host application. And the host application can be compromised according to the threat model of SGX. So an attacker can provide arbitrary data here, and this interface needs to be carefully protected. This is why our research focused on exactly this interface. So we looked how untrusted data is processed inside an enclave. And to do this, we developed a framework called T-Rex, which is based on symbolic execution, a very well-known technique to explore code paths in your application. We have some pre-processing to identify eCores, because these are the interesting points here for vulnerabilities. And we also do some symbolic hooks for common functions, because an enclave might execute some functions that are not of interest for vulnerabilities, and symbolic execution is a quite heavy analysis method. So for efficiency reasons, we provide some symbolic hooks for common function. And as you can see, we perform the analysis on enclave binaries, so we don't need source code, and can immediately also provide analysis for third-party enclaves. The main framework consists of using a symbolic explorer called Anger, which is a popular framework in this space. And we developed a number of modules to perform a symbolic execution for enclaves. In particular, we developed a pointer tracking module, because we wanted to see how pointers are propagated, as these are usually exploited for attacks, for memory corruption attacks. We emulate some of the special instructions, because SGX provides some new instructions which are not supported by Anger, the symbolic execution engine. And finally, we have some vulnerability detection modules, in particular control jumps, so that an attacker can control a jump target, a controlled write, that an attacker can perform dedicated and targeted writes to the enclave stack, and null pointer dereferences, because these play an important role for enclaves, where the attacker model is that the attacker is able to compromise the entire operating system, meaning that the attacker could also allocate the null page. And if there is a null pointer dereference in an enclave, this can be also exploited. And we actually found some of these vulnerabilities in enclave code. So after the symbolic execution runs, we get a vulnerability report, and the analyst then can construct an exploit on that report. So our evaluation was based on public enclaves. We were able to find, at that time last year, 7 enclaves. We now have a larger pool, but these were the 7 enclaves that we analyzed. As you can see, we have an enclave from Intel, which is example code that the other developers of enclaves could leverage. We analyzed a Rust SGX SDK implementation developed by Baidu. Then we have some research project like Talos, Wolf SSL. And then interestingly, we have 2 fingerprint drivers. So if you have a Dell, Lenovo, or HP laptop, you probably have these fingerprint drivers installed from Synaptics and Godix that also use enclaves to protect biometric data. And finally, we have the Signal app that is also using SGX for contact discovery. So let's look at this table. As you can see, we found exploits, meaning we found also vulnerabilities to launch the exploits for 6 of those 7 enclaves. We didn't find an exploit for Signal app. That seems to us a very well developed. But for all the others, we were able to find vulnerabilities. And you can see some of those have been fixed, especially the fingerprint drivers, of course, have been fixed through Windows update routines. And as you can see here, T-Rex was also able to find a number of vulnerabilities. So this doesn't map to 1 or 2 vulnerabilities, but like 3, 4 vulnerabilities inside these drivers, even if there is no source code available. If you are more interested in the exploit code, you can check out our GitHub page on this. If you, I think the presentation is recorded, so there should be a good way to write down this link if you are interested. Yeah, there have been some CVEs, of course, for the fingerprint drivers. And yeah, to conclude this talk, I want to give you a very nice example of vulnerabilities that we found. Here we have the Rust SGX SDK, which aims at providing a secure language for enclave development. As you know, Rust is a type-safe language which aims to have the same performance than C code. And Baidu Apache have developed an SDK based on Rust. However, you are still not safe against memory corruption errors because even type-safe languages, they include some native code. For instance, in Rust, you can have code that is marked as unsafe, where type safety is not applied. In this example code, the enclave is responsible for maintaining an SSL session, and there is a pointer to an SSL object which is located into enclave memory, and the enclave code validates whether this object is inside enclave memory. If it is inside, this means the object is good because it's encrypted, it's integrity protected. However, if it's outside, then it could be under control of the attacker. So if the attacker corrupts the pointer to the SSL object, injects our own SSL object, then this function validates, is the pointer pointing to an SSL object that is outside the enclave? Yes, it is outside the enclave, and it would return an error, which is this line, return error. However, there's a logic bug in this code from Rust, from the Rust SGX SDK, because if the memory object overlaps enclave memory and host application memory, then this function will not result in an error. This again means that the attacker controls part of the object. He can inject some malicious code pointers, in this example, virtual table pointers, which are used in C++, to hijack the execution. Because if the enclave code later uses this SSL object, then the attacker controls a virtual table pointer and then can run the attacks that we have seen before, like the ORED primitive, to gain arbitrary code execution and then steal cryptographic material. So the lesson learned here is that even if you deploy a type-safe language in trusted execution environments, there is still some native code involved, and there could be a logic error like we have seen here. And this could be leveraged by an attacker to compromise TE code. So to conclude some discussion, in our work, we leveraged symbolic execution because our main intuition was that enclave code is small and symbolic execution could be scalable for those. It worked for the enclave that we analyzed. However, for the fingerprint drivers, we already recognize that it's very hard to run symbolic execution on those fingerprint driver software. So currently we are looking into more efficient vulnerability analysis techniques like fuzzing. We also have found a number of vulnerabilities already. And yeah, we are currently looking into several projects that use SGX and hope that fuzzing can be used as a good way to find vulnerabilities beforehand. Another point is that currently there are not many mitigation technologies for trusted execution environments. And even if you look into the manuals of ARM or Intel, they all say, yeah, this is a classic problem. If there's a vulnerability, then this can be exploited. So we have seen that randomization has been applied to SGX code, but there's surely enough room to also improve trusted execution environments with more mitigation technologies like control flow integrity or data flow integrity. Our research so far has mainly focused on SGX, which was a very interesting target for us, but we also started looking into alternative TEE architectures, in particular those that are based on RISC-V. And it seemed that very similar attacks can be constructed for RISC-V TE architectures like Keystone and Cure. However, there is not much code available to us to really analyze whether existing enclave code for these architectures are vulnerable to memory corruption attacks. So we can only theoretically show that if there is a vulnerability, then there are exploit opportunities. So once these architectures get more popular, we will also look into automatically finding vulnerabilities and then hopefully improving the code quality of these enclaves. So hardware-assisted application is vital to implement trustworthy systems, especially considering cloud computing area. And however, it doesn't mean that if you deploy a trusted execution environment that you are completely safe. As you have seen in our research, 6 out of 7 enclaves by prominent players in the field have suffered from a number of vulnerabilities, even if TEE code is not as complex and large as a web browser. So we need to have some mechanism to find these exploits and also mitigate those exploits. And with that, I'm ready to take your questions.
Okay, thanks, Luca. Let's do this. Questions? There must be someone who has a question. Seems that I don't see in the chat any question. Seems that everybody is kind of
ready for lunch, yeah?
Yeah, exactly. Ready for lunch. No questions. Okay. Okay. As I mentioned, this this workshop is for free. So, and please use your time. And if you have any question now, you can just post it on the chat and we take care of that. Okay. So, Luca, thanks a lot for your talk. And I hope that there is one or another attendee who is interested in continuing discussion on this research. So let's then go to the next talk. Thanks, Luca. Thanks a lot.
Thanks.
Okay.
I have to leave for a lecture, so
Okay.
see you soon. But anyone is welcome to give feedback, also via email or other channels.
Okay.